Hello guys, welcome to another episode of Cuda Education. Today we're going to talk about the Vertex Buffer. Okay? Now, the Vertex Buffer is simply an area of memory that is reserved for vertex information. It is an area of memory assigned by the vertex buffer to store vertex related information as it relates to your computer graphics application. So the vertex buffer is basically an area of memory. Okay, so that's at the heart of what the vertex buffer is. Okay, so it's just going to store information in your it's going to store information in your memory that the Vulkan API is going to use to render your computer, whatever it is you're trying to present. So there are a couple of things that we have to do in order to communicate exactly what is in memory and what we need to do about it. One of the first things that we have to communicate is what they call binding description. Okay, and the binding description is simply data related information. So we're talking about, how fast should we load data from the vertex buffer into our application, the number of bytes between data entries, whether data entries are sort of segmented by each vertex or if it's segmented by each instance, right? So all the data related information is encapsulated in something called the binding description, and there are various variable types and things of that nature in Vulkan that deals with the binding description and the data related information. The other thing is attribute. Descriptions, right? Okay, so this now deals with, how to process the information inside of memory. So there are two in our case, there are two attributes that we work with. We work with position information, right? So in the case of a triangle, which is the example application we use, a triangle has three vertices. So the position information is talking about those three vertices. And then we also have color, right? So color is, how are we going to fill the triangle? So we have a color for each vertice in our example application. So there are three colors that are part of the triangle, and then they're combined together to make the full presentation of the triangle. So that's at the heart of what the vertex buffer does. It's managing managing and assigning memory for your Vulkan application, and giving you as the programmer the ability to communicate data related information, example, loading, right? And then how to process the information inside of memory. So position and color information. So how are we going to process the information inside of whatever is stored in here? You have to give Vulkan a roadmap on what is stored in there and how we're going to deal with that information. So that's one piece of the conversation. There is also another piece of conversation. This one we're going to call memory requirements. Okay. Now, memory requirements, it's simply dealing with, for example, allocation of memory, right? And type of memory. Now, as I've said in previous discussions, and I've discussed in the tutorials, Vulkan is designed to basically be open source because it's an industry consortium. The Kronos Group is an industry consortium that is designed to be open source and to work with many different pieces of many different hardware vendors. So the two main GPU vendors that I know of is NVIDIA and AMD. Okay, so with these different vendors, and I'm sure there are others on the market, their memory layout, or the types of memory inside of the GPU, I'm talking about hardware now. The types of memory inside of the GPU is there's a variety. It's divergent. They have all kinds of different memories, and Vulkan being an open source and fully explicit, fully granular, fully capable programming framework or API, has to be able to accommodate all of these different memory types, at least, if not accommodate them, at least, be aware of them and know what their capabilities are. So in my latest tutorial number 11, we discussed type of memory. And actually what happens is that we have to cycle through all of the memory types in the GPU hardware to find the memory type that we need for our application. So basically we cycle through the memory types, and then we get the index of the memory type that is suitable for what our application needs. And we save that index, that memory index, and then we use it for what we need to generate the triangle. So this is all part of the Vertex Buffer conversation. So, type of memory is very important. Of course, you have, the allocation of memory. Perhaps I'm not exactly fully sure, but I'm not sure if the allocation of memory is actually done under the memory requirements hat or if it's done under binding description. I actually don't remember, but between the two, there's allocation of memory. But the most important thing is that you have to manage the type of memory that you're using. Now, for our application, the memory that we need is memory that is visible to the host. And you have host and you have device. In parallel processing, in parallel computing, especially when you're dealing with CPU and GPU conversations or applications or things of that nature, the host is considered the CPU. So that's your Intel chip that does your general computing tasks on your computer, that runs the operating system, all that stuff. And then you have device memory, which is your the memory on your NVIDIA GPU or your AMD GPU or whichever other GPU there is on the market, right? So we have to cycle through, our application has to cycle through to make sure that whatever memory we use, the CPU can see that memory and do stuff with it. Okay, and the reason is that for this vertex buffer algorithm where we generate the triangle via the vertex buffer, for the first time that we do it with tutorial number 11, the data that we declare inside of our vertex buffer is actually inputted on the CPU memory. Okay, so it's inputted on CPU memory, and that's why when we're cycling through the types of memory on the GPU, we have to get memory that is host visible, which means that the GPU can see the memory that is on the CPU. That's my understanding of it. The GPU has to see the memory that's on the CPU, and then we do a process of creating a roadmap or mapping the CPU memory to the GPU memory. We transfer we do a mem copy to transfer the memory from the CPU to the GPU, and then we do the rendering from the GPU. Remember, all your presentation and everything is being done on the GPU. So even though it resides on the CPU, the GPU has to be able to see it, access it, or get copies of it, and then render off of the GPU, right? So, not to get too ahead of myself, but the next iteration or the next opportunity in terms of optimization and making sure your frame rates are as high as possible, your graphics is as good as possible. The important thing to do is to in the next optimization, not in this tutorial, but in the next tutorial, is to have the data inputted natively on the GPU itself. So instead of putting it on the CPU and then doing a mem copy over to the GPU, you put it natively on the GPU so that you don't have to do that mem copy operation, and therefore there's less latency and less operations need to be done, and you could maintain a higher frame rate. Now, obviously with a triangle, it doesn't really matter, and you're not going to see any noticeable performance difference. But if you're doing industrial level computer graphics applications, for example, a video game, or some kind of military simulation, or a real estate simulation or something, and you have thousands of operations going on and things of that nature, you don't want to having to be mem copying all that data over to the GPU before the GPU can render it. So that is another conversation in the whole situation of the vertex buffer. Another thing that we have to quickly discuss is the graphics pipeline. Okay, so from my understanding, the graphics pipeline is simply a series of discrete stages that eventually result in presentation to the screen, right? And there's a whole bunch of operations, and there are a whole bunch of constraints and guidelines and things you can and can't do as it relates to the graphics pipeline. But in tutorial number 11, when we're converting our code from hard-coded information over to using the vertex buffer, we have to kind of change the graphics pipeline to say, hey, graphics pipeline, now you have to use the vertex buffer to basically get your information and process what you need to process to get to get to presentation. So updates to use vertex buffer. All right, so I mean that's as much as I'll say about the graphics pipeline for now, but basically you want to update the vertex buffer to use it for update the graphics pipeline to use the vertex buffer. And then lastly, what I want to talk about is the command buffer. Okay, so the command buffer is from previous discussions and also in tutorials, you'll see the command buffer is pretty much pre-planning or pre-declaring all the operations that you want to do before Vulkan actually has to do it. So you're basically communicating to Vulkan, hey Vulkan, these are all the operations I want you to do when the application is running, and Vulkan has full and complete visibility in what's coming next. So what is it that you want to do, how many times you want to do it, when you want to do it, how you want to do it, all that good stuff. So one of the great opportunities of the Vulkan API is that because you pre-communicate, right? You pre-tell, pre-communicate all the things that you want to do. Vulkan, upon compiling and running the application, it can make certain optimizations because it knows what's coming next. So unlike in OpenGL where things, every new thing is a complete surprise to the OpenGL API or the framework, in Vulkan, it knows everything that's coming up next ahead of time. So it can make certain optimizations that help you to maintain your frame rates, maybe not have the GPU work as hard and all of that stuff, because it kind of knows what's happening next. So the command buffer is a very important piece in the Vulkan API, and you have to update to use the data in Vertex Buffer. Okay, so basically, unlike the hard-coded version of what we did, now we have to basically rewire the command buffer to say, hey, command buffer, we actually have a Vertex Buffer, and the data that you want is in there, and you need to use that data in order to do what you need to do. So that is pretty much a good general overview of the Vertex Buffer situation. Now remember, guys, this is tutorial number 11, and I will put a description. I'll put a link in the description below for that tutorial. You can get it on the Amazon ecosystem. So basically, the YouTube link is embedded inside of the Kindle ebook, and you'll get an actual full discussion on a programmatic level, because the idea is that you have running code on your computer that you could tinker with, that you could see all the modifications that I'm making and all the things that I'm doing. So tutorial number 1 gets you to install the Vulkan API on your computer, and then gets you to have running code through the Visual Studio IDE or what have you, so that as we step through the different tutorials, I'm not just talking and you're not just looking. You actually have the code running on your machine. That's the goal, that you have the code running on your machine, and then you could experiment and see for yourself and make modifications as you see fit, and do as you will. Another note also is that for tutorial number 11, I actually had to upgrade to Visual Studio 2019 Community Edition. So the previous tutorials all the way up to tutorial number 10 has me running on Visual Studio 2017 Community Edition. I upgraded to 2019 Community Edition for reasons completely unrelated to the Vulkan API or these tutorials or anything like that. But basically, I had to I had to upgrade my environment. So it's Visual Studio 2019 Community Edition. I haven't really seen much change in anything that I'm doing, or any processes or procedures or anything. So if you're still running 2017 Community Edition based on the previous tutorials, I don't think it's going to be an issue. But of course, in programming, things are always changing and things are always moving. So I just need to declare that up front to you guys, and I hope that it's not going to be a problem when you're trying to run code. Again, you want to get tutorial number 1 done, and have, this is a Windows environment, of course, and have the at least the baseline program running on your machine up until I think it's tutorial number 9 or 10. We have a new program that's basically the swap chain recreation, where we're able to adjust the window size of the triangle, and the program can handle it gracefully. We could adjust the window size, and we could minimize the window, and the program handles it gracefully with no problems. So off of that code, now we try and use the vertex buffer, because up until that point we've been hard coding in the vertex information, so the vertices of the triangle and the color information, we've been hard coding it in. But the vertex buffer situation now is we're no longer going to be hard coding in the information. We're actually going to be using the vertex buffer, and I believe the reason why we delayed using the vertex buffer is because I mean, it was already a lot of work just to get a triangle on the screen, and the vertex buffer is a whole nother conversation in and of itself. As you can see here, there's a lot of other considerations and things going on. So you have to it's a whole beast unto itself. So yeah, I guess the priority is to get the triangle on the screen, and then we could discuss more complicated things and more complicated things later. This code, I don't even know. I know it's 900 lines plus code, but I think with the vertex buffer, it's more than that. So it's 900 lines plus, and the reason for that is that the Vulkan API is interested in giving you maximum control over your situation. So hardware, software, options, settings, memory, parallel processing, threads, all that stuff. That's what the Vulkan API is about. It's about updating computer graphics for the parallel computing world. OpenGL was imagined and developed for a time when I guess computers or CPUs or GPUs didn't really have parallel processing, so multiple lines of work, multiple threads of work, and all that stuff. So ever since parallel processing came on the scene, OpenGL has been basically trying to manage a bad situation or a less ideal situation as best it can. But of course, you're making compromises, and you're basically using high-level functions that don't give you full control over what's happening behind the scenes, or it's window dressing an operation as one thing when really behind the scenes it's doing something completely different to manage the situation. So the Vulkan API is a complete reset of computer graphics and how software interacts with hardware. So it's a wholesale thing. So it's more verbose. It's a lot more lines of code, but the understanding, from what I understand, is that once you get the basics down, once you get that triangle on the screen, then anything else you want to do, and it's a lot of lines of code, but once you have the sort of the default settings, once you have the default settings down and everything is set up, and you kind of have a good idea of what things are and where they are and what they're doing, that anything else you want to do in the future is pretty much straightforward, because you have things in place in terms of the structure, or the framework is already in place. So to do more complicated things or more extensive things, it's not only easier and requires less code, but it's also inherently optimized better, because you have control over pretty much everything. All right. So that's my sermon today for the Vulkan API. Definitely check out tutorial number 11. Definitely tell your friends about Vulkan. I recommend, if you have friends, that you guys get together and try and tackle the Vulkan API together. It's a lot more fun that way, and it's a lot more rewarding. The the computer industry, the programming industry is so fragmented. It's not even funny, but computer graphics is one of the few areas where there is a certain level of cohesion and almost funneling, where basically if you master the Vulkan API, you pretty much are going to be in demand, employable for the foreseeable future. And it's not like you're going to be obsolete anytime soon, right? Because between all that's going on, virtual reality, augmented reality, computer vision, just digital tools and things of that nature, the ability to put a pixel on a screen is golden in today's world. So make this a group thing. Tell your friends about it. Get them to get the tutorials too. Work through the processes. This is a Windows-based thing, which kind of makes sense because the GPUs are mainly focused on Windows, right? So and that's why gaming is mostly focused on Windows, because that's where the GPUs are, and that's what they're synced up to run most effectively on. So the world is changing, and it's changing really fast. So get on top of it. Get your friends to work with you, and prepare yourself for the future, because it is the future. Anyway, I think this sermon has gone for too long. Definitely check out all the links below. I have links to the Cuda Education website, to tutorial number 11, to all things that are good and wholesome for everyone. So thanks for watching. Have a great day and be safe.